Welcome to the Explainer. Deep learning can feel a lot like magic, right? But it's not. It's actually built on a handful of really elegant core ideas. Today, we're going to pull back that curtain. We're going to break down those fundamental principles and build our understanding completely from the ground up. So here's our game plan. We're going to start with the language machines use to see data, which is all about linear algebra. Then we'll dive into how they handle the real world's messiness using probability. After that, we'll get into the engine of learning itself, optimization, before we tackle the huge challenge of generalization. And finally, we'll uncover this really fascinating assumption about data that makes all of this even possible.
All right, first up, the language of learning. Look, if you want to get inside how a neural network thinks, you've got to start with the language it speaks. And for modern AI, that language, hands down, is linear algebra. The most basic building block is something called a vector. Now, it sounds all technical, but really, it's just an ordered list of numbers. That's it. Think about an image. To a machine, what is it? It's just a long vector with the brightness value of every single pixel, one after the other. This is how we translate our world into a format a computer can actually work with. Okay, and this is where it gets really cool. We can actually visualize these vectors as points in space. So each number in that list becomes a coordinate along a different axis. A vector with 3 numbers, that's just a point in 3D space. But an image with 1,000,000 pixels, well, that's a single point in a 1,000,000-dimensional space. And just like that, a data problem becomes a geometry problem. And, like any language, this one has its own grammar, its own notation. This is the shorthand that lets researchers communicate these incredibly complex operations really efficiently. Things like grabbing one single value out of millions, or flipping an entire dataset on its side with what's called a transpose. It's all about speaking the same, very precise language. Okay, so we can represent data as these super precise points in space. But let's be real, the world isn't precise. It's messy, it's uncertain, and that brings us to our second big idea, reasoning with uncertainty. This is all powered by probability. So how on earth does a machine quantify doubt?
Well, the answer is probability theory. And this quote just nails it. It's an extension of logic to deal with uncertainty. So instead of thinking in these black and white, true or false terms, probability gives us a formal, rigorous way to reason about all the shades of gray, the likelihood that something is true. You could almost call it the mathematics of doubt. But how do you actually put a number on uncertainty? For that, we use a concept called Shannon entropy. The short version is, it's a measure of surprise. If an outcome is super predictable, it has low entropy, not much surprise. If it's totally up in the air, like a fair coin flip, it has really high entropy. It's a brilliant way to quantify what we don't know. And this is directly, and I mean directly, tied to learning. See, an untrained model is totally uncertain. Its predictions are basically random guesses. That's a high entropy state. The whole point of training, the entire goal, is to crush that entropy, to make the model more and more certain until its predictions go from random noise to a confident, deterministic answer. Okay, so a model can represent data. It can reason about uncertainty. But that leads us to the biggest question of all. How does it actually learn from the data? Well, this is where we get to the engine room, optimization. The whole training process, literally everything, boils down to this one question. We start with a cost function, which is just a fancy way of saying a score that measures how wrong the model is. So learning becomes a hunt. We're hunting for the perfect combination of internal settings, or parameters, that will make that error score as low as it can possibly go. It's exactly like trying to find the absolute lowest point in a huge, fog-covered mountain range. So how do you navigate a landscape like that when you're blind? You use a tool from calculus called the gradient. And it's brilliant. Think of the gradient as a compass that always, no matter where you are, points in the direction of the steepest uphill slope. So if we want to find the bottom of the valley, well, we just take a step in the exact opposite direction. And this gives us this incredibly simple but powerful process called gradient descent. It's just a loop. You start somewhere, you calculate the gradient to see which way is up, you take a little step in the opposite direction, downhill, and then you just do it again, and again, and again, and again, until you settle into a valley and you just can't go any lower. But of course, it's not always that simple. In these unbelievably complex landscapes inside deep learning models, the biggest problem usually isn't getting stuck in a small valley. The real challenge is getting stuck on a saddle point. Just look at the slide. It's this tricky spot that looks like a valley from one direction, but a ridge from another. Our little algorithm can get really confused on these flattish areas, and that can grind the whole learning process to a halt. Now, finding a minimum on your training data, that's just step one. The real goal, the true art of it, is making sure your model actually works on new data it's never ever seen before. This is the art and the science of generalization. This is what makes a model useful. This means we have to keep our eye on two different scores. There's the training error, which is how well the model does on the data it's already seen. We can usually push this number way, way down. But the real report card is the test error, how it performs on brand new data. A great model isn't one with a zero training error. It's one where that gap between the training and test error is as tiny as possible. So how do we close that gap? Well, we lean on a really, really old idea, Occam's razor. The principle is beautiful in its simplicity. If you have a bunch of explanations for something, the simplest one is probably the right one. In machine learning, this means we should prefer simpler models. And why is that? Because a really complex model can just cheat. It can memorize every little quirk and bit of noise in the training data. A simpler one is forced to find the real underlying pattern. This slide just lays out that classic trade-off perfectly. It's a balancing act, and it's all about the model's capacity, which is just its complexity. Just look at the table. If the capacity is too low, the model is too simple. It underfits. It can't even learn the pattern in the first place. But if the capacity is too high, it overfits. It memorizes the training data perfectly, creating this huge gap when it sees the real world. The whole game is about finding that good fit right there in the sweet spot. All right, our final section. This one gets a little more philosophical, I have to admit. It uncovers this really profound assumption that we have to make about data itself. This idea, the manifold assumption, is pretty much the secret sauce that lets deep learning actually work in the first place. I want you to really think about this for a second. Imagine an image that's 1,000 by 1,000 pixels. That's 1,000,000 pixels. Now, if you just randomly assigned a color to every single one of those 1,000,000 pixels, what do you think the odds are that you'd get a picture of a cat, or a human face, or anything at all? The probability is basically zero. It's just not going to happen. You'd just get TV static every single time. And that observation leads us to the manifold assumption. The idea is that meaningful data, images of faces, clips of human speech, all the stuff we care about, it isn't just scattered randomly everywhere in that massive space of possibilities. No, instead, it's all clustered together on a much simpler, lower dimensional structure, a manifold, that's embedded inside that bigger space. It's like discovering that all the cities in the world are built along a few major highways, not just sprinkled randomly across the globe. And that is the secret. That's why this all works. Because real-world data is so highly concentrated, a deep learning model doesn't have to understand the entire universe of random noise. Its job is way, way simpler. It just needs to learn the shape of that winding road where all the meaningful data actually lives. This is what takes an impossibly huge problem and makes it totally manageable. Which leaves us with one last, kinda provocative thought to chew on. If all the data we find meaningful, faces, language, music, if it all lives in this tiny structured fraction of all the data that's possible, then maybe all meaning is simply structure that's hidden in a vast sea of noise. And maybe the process of learning, maybe intelligence itself, is just the act of discovering that structure. Something to think about.